Good morning, good afternoon, and for those of you joining us long after your workday, good evening. Welcome to Keysight's PathWave Design RF Design Week. My name is Richard Duvall. I'm a Senior Marketing Engineer at Keysight, and I'll be your host for the second of two exciting webinars this week, examining RF and microwave circuit and system design challenges and solutions. Today's webinar is the second webinar in our RF Design Week and is titled Learn About the Most Advanced RF Phased Array Design and Modeling Platform. Now let's move on to the presentation. Joining us today are three speakers. Tom Lillig is the General Manager for PathWave Software Solutions. Tom's talk is titled Evolution of System Simulation. Mark Lombardi is a Satellite and Space Workflow Solution Architect. Mark's talk is titled Escape Velocity Using Modeling and Simulation to Enter a New Orbit. And Ian Rippke, who is the System Simulation Product Manager. Ian will talk about PathWave System Design 2022. Ian's talk will be followed by the question and answer session. So welcome all, and Tom Lillig, why don't you get us started?
Hi, my name is Tom Lillig, General Manager of Keysight's PathWave Software Solutions team. Welcome to the PathWave Design 2022 RF System Design webinar. I'm going to do a quick kickoff before turning it over to a few of our experts to talk about our solutions in more depth. The system simulation market is rapidly evolving, but of course system design is not new. In the electronic space, system simulation starts with transistor models. Part of those models are then used as the basis to do circuit simulation. Parts of the circuit models can then be used to simulate subsystems like circuit boards or RF front ends. And then parts of these models can be combined to create ever-increasing system-level simulations. It's important to note that at each of this step in the ladder, we can only take portions of the lower level into the next level, or we'd run out of processing power. By themselves, these simulations are very valuable because they are able to help guide our designs and make trade-off decisions without having to build a physical product. But simulations also help guide requirements, which typically flow in the opposite direction. We first want to know how we want our products to behave in the real world in the environment, and then we design our products accordingly. Finally, we build our products, and at each level we have to test them to ensure that they meet the requirements before we can move to the next level. So again, the key here is that as you move up in the stack, you typically have to make tough trade-offs with accuracy, compute power, simulation time, or all three. For example, if we're designing a self-driving car and we want to simulate how it will behave in a real-world environment, we won't simulate every transistor of every car on the road. And this applies to other types of physics too. Of course, we don't simulate the physical behavior of the molecules of the roads and the trees and the people, pedestrians, even though the lower level simulations are indeed based on those molecular models. To add to the problem, our systems continue to grow in complexity at an exponential rate. The system might be a self-driving car, or a driving environment with multiple cars, pedestrians, stoplights, etc., or it might be a battlefield with a variety of jammers, radars, and commercial RF devices all in the same environment. Putting these systems in place without simulation would be a nightmare. We would need to make sure that our communications are secure and our products are safe and effective before they are deployed. This is where high-performance cloud computing comes in. Until recently, cloud computing was optimized for things like e-commerce. Now, Amazon, Microsoft, and others have added very high-performance compute machines to their clouds, which enable highly complex simulations. We can now apply an almost limitless on-demand amount of computing to these problems. This means that we could take on larger, more complex simulation challenges, and that our simulations can have higher fidelity than we ever imagined. This has enabled a surge in model-based engineering, or MBSE, and digital twins. Neither of these concepts is new, but both are becoming more common and more practical with the evolution of the cloud. For example, the market for digital twins is growing at 40% per year. Keysight is a leader in simulation, especially in the areas of wireless circuit and system simulation. However, simulation by itself is not very useful. After simulating your system, you're going to build a prototype and you're going to want to see how it works and where your actual products differ from the simulation. And then what do you do when the test results don't match the simulated results? Was it a defect in the way the device was manufactured? Was there an error in the way the device was tested? Did the test equipment use different measurement algorithms than the measurements made on the simulated domains? There's just a lot of questions and a lot of variables you have to consider. It becomes very difficult to correlate your simulated results and your real results. This is where Keysight shines. As a leader in design, validation, and manufacturing tools, we don't just help you get through one phase of your development cycle. We help you go from concept through design, validation, manufacturing, and even post-production operations. In an effort to ensure interoperability of various tools, Keysight has created PathWave. PathWave defines common interfaces, common data models, common measurement libraries, and reusable waveforms. This ensures that the various parts of your workflow can interconnect with each other. This includes both Keysight tools and tools from our partners. Next, you're going to hear more details about how Keysight and our partners are working to improve your development flows. Enjoy.
Hello, my name is Mark Lombardi. I am a space and satellite workflow solution architect working for Keysight Technologies. Here today to present escape velocity, using modeling and simulation to enter a new design orbit. The intention of this paper is really to highlight some of the unique challenges in the space industry today and how modeling and simulation and digital transformation as a whole can help move the space industry forward and accelerate design and innovation. These are exciting times in the space industry. So much change and innovation. We have reusable rockets. No longer are the stages necessarily falling into the sea and being wasted. Companies like SpaceX are relanding those stages and ultimately driving down the cost of getting into space. We're seeing innovation in small sats, especially in low Earth orbit, where the designs can be scaled differently. They don't have to last for 30 years like the old geosynchronous satellites did. That means you can make trade-offs based on less radiation exposure, maybe use more off-the-shelf components, even use components that haven't been space tested yet. From the technology side, we see optical crosslinks enabling high bandwidth between these constellations, effectively creating a network in the sky. Phased arrays are a key enabling technology when you have low Earth orbit satellites and need to track them. Having non-mechanical solutions that can be integrated into consumer products, become a key enabling feature for these new applications in space. And lastly, the demand for ever more bandwidth and ubiquitous anywhere connectivity is driving the satellite industry to higher frequencies where they can get wider bandwidths and higher data rates, as well as more complex modulations where they can now realize high data rates. But with these technologies comes complexity. Systems that are no longer linear, they're nonlinear, and they cascade in nonlinear components working together. No longer are the margins available that once were available in going to space. It's an entrepreneurial effort, and so every penny, every bit of efficiency, every bit of design that is done has to be on point and really points to the idea of doing as much as can be done early with digital transformation. I'd like to now delve a little bit into the workflow. If you think about design from concept all the way through to operations, let's say putting a satellite in space and actually getting data, if it was imagery or other missions, you have a beginning and an end, and usually that was thought of as a linear process. Then in the 90s, or maybe even a little earlier than that, the concept of there were similarities between the early parts of that phase and the latter parts, and the V diagram was built. And I think of it from the test perspective as something like a test that might be developed and done in early R&D could be leveraged or inform the tests that are done later in production. A nice build that's recently come out in 2020 is from Boeing. They've built out what they call the MBE, or Model-Based Engineering Diamond. And what I like about this is it builds from the V. Think of the V at the bottom as being the workflow of the physical development, but it gives equal weighting to the digital design or the digital twin that moves along and develops along with the physical design that you're building. What's nice about this is the data or the digital twin can help inform the physical test, the physical development, and it's valuable all throughout the design. So people typically think of simulation early in the development cycle. For example, when you're just starting to think through the plans, try out some designs before you actually start to physically build the design. But people leave the digital design behind many times as they move forward. In this vision of the future and design, what we see is moving that digital design along, or the digital twin along with the physical development. And in this case, you could look all the way to the endpoint. For example, they mention virtual support that goes along with the physical device that is being supported. So it gives you another tool, and you haven't left behind all that investment that you've made early in developing your digital twin and your digital transformation, that carries through the whole development cycle. From here, I'd like you to consider another build, and that is if you do now see the value of running the physical design and the digital design or simulation along with the development cycle, we can look at this model in yet another way. We can take the ends of that model, which somehow indicate inputs and outputs. Of course, you start with an idea and you end up with hopefully a product. And in this case, a satellite, let's say. But there's more to it, that everything that's come before, if we keep the data, if we keep the designs, and in this case, those two lines are indicating the physical and the virtual design moving along together throughout the life cycle. You see, ultimately, you can use the data that's in the field, the system that you actually deploy, then to inform and feed the next design phase. What's also important to realize is once you have this concept of data that is persistent and information that is persistent and leverageable and usable throughout the design cycle, that any time is a good time to start. For example, I could start collecting data today on a manufacturing process or a part that's in manufacturing. That data then could inform as you move forward to the next design, as long as you have that data and it's a format that you can look at again, you can put back into models the data actually maybe has statistically refined that model, so you even have more confidence in the model, it now informs the next design and speeds up that development cycle. What's important here is the data is available. In this case, we're showing it as a cloud being the central repository, and then the loops going in and out, so that data can be pulled in and out at any part of the development. And it can be used both in the direction of the digital design, informing some part of the physical choices that are made in the actual design. And it can actually be used the other way, where the measurements on that design you've put in place, that component, that part, that subsystem, then can inform the models and even make them better. And we populate that by showing the different tools, both software and hardware, and showing that interface that test equipment uniquely provides, which is a bridge, or some people might call it a digital thread, that allows physical measurements, physical things to then inform the digital twin. The digital information, or the digital models and simulations, can be used as information that can be put into a software-defined piece of test equipment and allow that test equipment to fill in for the physical parts that may not be available yet. So you can see, if you use this correctly, what you can do is move very quickly and not get stopped because of a delay in either the physical or the virtual design, that one can inform the other, and you can move back and forth efficiently between the two as long as you're connecting the data. One way we've talked about this is in the idea of reducing risks. Space has a lot of risk associated with it, and really one of the fundamental changes is moving to higher risk profiles, some would say. The other way to think of it is, there's only so much risk you really do want to take it on. And over time, what you hope is that your design starts to get better and better. You get more confidence, and your risk goes down. And that's shown here in, as you move all the way to operation, your confidence in the system, of course, goes up. One of the things that we can do with digital twins is we can start to now move that confidence level up, because we start to have more confidence in the models. They're persistent. They're there whenever we need them. We're checking them throughout the development cycle. And you can either think of it as a shift left, some people think of it, but I think the better way to think of it is the way the Air Force Research Laboratory talks about it, and that's this idea of reducing risk or increasing confidence in the design, ultimately then leading you to faster development cycles and quicker turns to the next design. We see in the space industry, and actually in many industries, there's a unique inflection point that we're entering with model-based engineering and model-based design. The needs there, obviously, the risk associated with some of the space programs, the complexity, the use of off-the-shelf components, the use of components that haven't been tested in space yet. So how do you get confidence in those? The needs there to have digital representations of these systems to help increase confidence, reduce risk. The enablers are starting to come into place. We have more computing power than we've ever had before. We've got cloud storage or cloud access where people can interchange or share or keep the data persistent. The digital twins are coming of age. They're getting better and better. The models are getting better. They're getting tied all the way back to physics. And that's always been possible. The problem is that it takes time and it takes lots of computing power to do that. Now that's falling into place. And the results for following digital emission engineering or model-based engineering and model-based design is you can learn early or fail fast. You optimize systems. In other words, in the design phase, you have more time in virtual design and simulation where you can optimize the design, and really you can focus on your core value that you're bringing to the system. So instead of spending time on the tools and integration, as Dr. Roper talked about, we're spending our time engineering and adding value to the project we're deploying. I'd like to end on a thought, and it's a quote from George Box. The quote goes, "All models are wrong, but some models are useful." And I think that's a well-accepted understanding that models can inform. They're only as good as the models, and they're only as good as our understanding and use of those, application of those models. But I like to consider that if you use models correctly and you use models and simulation throughout the life cycle, those models then become lasting and persistent, and they inform the next development phase. And so I'd like to leave you with a Mark Lombardi quote, and that is, "All models are wrong, but persistent, authoritative, intersecting models are very useful." With that, I hope you have a good day. Goodbye.
Hello and welcome to our PathWave System Design 2022 preview, part of our RF Systems section of our PathWave Design 2022 launch event. We're excited to have you here and very excited to share some of the new features that we've been working on that are coming in our PathWave System Design 2022 release later this year. I'm going to talk a little bit about trends that are impacting system-level design and how those affect system designers and where PathWave System Design fits into that workflow. But then we'll really get into the exciting part, which is covering new features in phased array analysis, new capabilities in our radar system simulation, and enhancements to our PathWave System Design and PathWave Vector Signal Analyzer integration to bring you a connected workflow of Keysight measurement science. So thanks again for joining us, and we hope you find some exciting features that you'll be able to use in your future system level design. One of the biggest design trends in modeling and system level design happens to be something that's not really new at all. The idea of model-based engineering, or the more formal implementation of model-based systems engineering, is really reaching its zenith here in this current era. And that's being driven by a desire for something called a digital twin. A digital twin means different things to different people, but generally it's a representation that's physics-based of an actual system that's been developed through system modeling and simulation. The idea is that you can exercise a digital twin the same way that you would its physical equivalent. Well, why is this important? Well, as we saw, when you put something in orbit, it's not easy to go back and try to test modifications. So in the past, you've had to build an entire other physical representation. Well, the idea of having a simulation-based model where you can exercise different conditions and different types of behaviors, test out new ideas, or even swap out parts virtually is extremely attractive for extending the life cycle and the duration of missions and operations and overall very complex systems. And now not everything is going to be a full digital twin of its physical representation. We might have a digital twin of the communications link, which offers the same capabilities, but really is a representation of just one piece of the overall system behavior. So, as I said, these are not new concepts, but why now? Why is this such a big topic, and why is it growing so quickly? Well, the systems are increasing in complexity extremely rapidly. The other thing that's happening is compute power is increasing exponentially. Cloud computing is giving us access to a lot more processor capability than we would have had in a standard internal company-based server in the past. So the complexity of these designs is matched now by the computing power that we have available. And driving this digital transformation is the interest in ultimately reducing cost, bringing products to market faster, and being able to extend their life cycle through updates and upgrades without having to create entirely new products. One of the fundamental things behind modeling and system engineering is the idea of a universal source of truth. And at Keysight, we really see that benefit of having a source of truth coming from our common measurement science and our common measurement techniques. We deploy these across both our simulators and our test equipment so that you have confidence that what you simulate will perform the way that you measure it with Keysight equipment. And so here's a graphical representation of our PathWave System Design platform and how it already operates as a model-based engineering or digital engineering workflow. You can see here the ability to bring data in from numerous sources, both external, like partner products, or from other products within the Keysight domain. We've got measurement-based models, circuit or simulation-based models, electromagnetic models. We have the ability to model channels and terrain and other types of characteristics, both in our product and through partners such as the ANSYS SDK product. And we also have the ability to do measurements of those either in our vector signal analyzer software or with built-in calculations. We can include scripting or additional post-processing in tools like MATLAB or Python. And once you've done this type of analysis, it's available to download directly to Keysight sources and analyzers, either for additional use in the testing domain or for types of analyses that just aren't possible within the simulation environment. So this already is a representation of how customers can implement a digital engineering flow directly using PathWave System Design. So now let's get into the exciting parts of the presentation and show you some of the new features that we're bringing to PathWave System Design 2022. We already see PathWave System Design as the most advanced RF phased array design platform on the market, allowing you to very rapidly architect and simulate the most complex and advanced phased array designs. We've made it extremely flexible and easy to import any kinds of antenna patterns and really give you the ability to verify these antenna and array designs with circuit level accuracy, whether that's measurement or behavioral models, and also bringing in that critical RF modeling, including interactions between the components, circuits themselves, and the antennas. Building on those existing capabilities, we've added an exciting new feature for channel-specific impairments. This is really critical in the area of phased array design because in most cases, the transmit and receive channels are going to be different, maybe different components or different types of settings, depending on where they are in the array, particularly with very large array structures. So with this new feature, we can set up specific groupings of types of components within PathWave System Design. These different groups can have different parameters, including different statistical variations to represent realistic behavior when you do something like a Monte Carlo analysis or looking for behavior over the lifetime of an array. But this wouldn't be very useful if you had to try to set this all up directly from the standard user interface. So we've added a visualizer which gives you the ability to preview exactly where these groupings are structured and validate how you've implemented this in your plan. This is supported for both our frequency domain phased array analysis as well as our time domain data flow capability for simulating phased arrays with modulated signals. Let me show you exactly how this works with a brief demonstration. In this demonstration, we're going to show how these RF amplifiers can be used in an array. We're starting from the basic phased array RF amplifier transmit template. You can see that we've got a number of amplifier components, including our original amp RF, and the new phased array RF amplifier component. If you look at the parameters of the amp, you'll see that it only has one value for all of the different RF parameters. However, if you go into the array amplifier, we're going to find how we can set up different groups. Going to the Frequency tab, you'll see this new group box. Clicking on Manage Groups, we can now add a number of different groups to this amplifier component. In this case, we've added 3 groups. Going back to the parameters section, we see that the group names now appear, and we can see the 3 distinct groups. We can now assign different values to each of the RF parameters based on which group they're in. In this case, we can set an array value for noise figure of 5, 2, and 3, corresponding to the different groups that we're using. In this case, we've already set up an array RF amplifier, and we've used 3 names here: center amps, inner amps, and outer amps to represent their location. The group map tells us where these go, and we'll come back to that in just a moment. But you can see we've added the same gain for each amplifier, but different noise figure, 1 dB compression point, saturation, IP3, and IP2 values. We're able to visualize this by using our phased array visualizer. By default, this was used to show the element IDs, and they're all described with the same figure. But you'll notice now there's a new option called Group IDs. If we select Group IDs, you'll see the array components now are listed by the number of group that they're in. You can also choose the option Color Groups in order to clearly indicate which group elements are in which locations. In this case, we've defined this group map using a simple script in the equations section. This gives us an easy way to set which components are at which array positions. Once this is done, you can perform all of your traditional phased array analyses, such as the beam pattern, phi cut, theta cut, and the phi cut directivity plot. So these new capabilities are essential in order to accurately predict realistic phased array analyses. One of our biggest areas of investment in this release has been in our radar systems design capabilities. As you know, radar designs are not simple systems. They're very complex with a number of RF, analog, and digital components, especially on the signal processing side, but with also advanced capabilities in the RF domain as well. Setting up such a complex system has been a challenge in the past, especially including numbers of different targets and scenarios and trying to test that radar in real-world conditions. What we've brought in this release is a much simpler radar system configuration with improved visualization and the ability to easily verify that system performance against your mission parameters. Let me start by talking about how we've improved the system configuration. We've got a brand new user interface that allows designers to very easily choose from different simulation configurations and then choose what types of environmental and technical modeling factors they want to include in the analysis. This could be different objects, signals, jammers, clutter, or other types of non-idealities that need to be modeled in the system. Once the user configures this, it's going to automatically generate a system-level schematic that will represent all of the things that were chosen and configured in the user interface. The user can run this simulation directly from the interface without ever having to manipulate the system design schematic itself. But for advanced users or for advanced configurations, that schematic is there and available for different types of analyses. In the past, trying to configure complex scenarios, numerous targets, and their motion from a schematic has been one of the biggest challenges of trying to accurately represent your radar system. Well, those days are gone because we now have, as part of this radar user interface, the ability to easily configure numerous objects, what type of object they are, their positions, their motion, and ultimately visualize the actual behavior throughout the scenario, including the ability to navigate in a two-dimensional representation of the model itself, zooming in, checking for conditions and certain behaviors to make sure that your scenario represents exactly what you want your radar system to model. And we're very excited to have partnered with ANSYS and their STK visualization capability in order to provide this to you. This is going to be available in our aerospace and defense advanced visualization product coming when PathWave System Design 2022 ships later this year. And speaking of our partnership with ANSYS and the STK product, I want to remind you that PathWave System Design has a direct interface to the STK software. So when your radar system has reached a level of complexity where you need additional capabilities, the 3D kinematics, additional dynamics, or much more complexity of your scenario or mission, we still have the integration available to bring those scenarios directly from the STK software and link those into PathWave System Design. This is an easy way for system design users to be able to take advantage of complex mission and scenario modeling and give a much more detailed digital design and digital engineering representation of the overall system behavior. Now let's head to a demonstration and see how this looks in real life. This type of advanced radar analysis is possible using PathWave System Design, but this schematic can easily be created with our new radar GUI. Within the UI, accessed from the radar tab, you'll be able to set all of the different parameters of your radar system design. The radar signal lets you choose the modulation type, phase coding, as well as radar signal processing parameters, details about the carrier frequency, output power, wavelength, and sample rate. Clutter can be added as well from multiple components of our radar library for different types of clutter and effects. The key is adding objects to this as well. You can add multiple targets using the UI, and you can configure the type of behavior, whether a target, a jammer, or the type of vehicle, such as a drone, ship, facility, aircraft, or a ground vehicle. But the benefit of this new UI includes advanced visualization. We need to be able to see whether the configurations that we've entered are really what we're trying to model in the scenario. Each of the targets can be given a position, altitude, speed, and additionally, more waypoints can be added to include turns and adjustments to parameters. For example, in the fighter case here, we're able to add acceleration, turn radius, and multiple dynamic behaviors, as well as additional waypoints. Once the visualizer is launched, you can see each of the targets that you've defined as well as your radar system. You can then put this into motion to see the actual trajectory and behavior of each of the objects that you've defined in your system. This is made possible through the integration of STK by AGILE and ANSYS company. Using their advanced visualization capabilities, we can provide users with a dynamic behavior and understanding of their scenarios. As I mentioned earlier, one of the ways to achieve a universal source of truth in your simulation and test methodology is to make sure that you're using the same measurement science behind both your simulation and your test environment. PathWave System Design has a very tight integration with our PathWave Vector Signal Analyzer product. This gives you the easy way of representing your measurements in the simulation environment using the exact same interface that you'll be using in the testing environment. This is an integrated workflow where configurations of your PathWave System Design analysis directly create the required setups that are used in the Vector Signal Analyzer. This lets you take things directly from the simulation environment into the lab testing environment using identical configurations and keeping that common measurement science available. In PathWave System Design 2022, we've enhanced the connections to the Vector Signal Analyzer software and tightened the integration for an improved user experience. What this means is much faster measurement initialization. So going from the point where you press the simulate button in System Design to seeing your results displayed on the Vector Signal Analyzer is greatly reduced and much more like the behavior of just running in PathWave System Design natively. We've also added new exciting capabilities to use the Vector Signal Analyzer not just as a sink, but also as a source back into your PathWave System Design analysis. The new VSA link component takes data out of PathWave System Design simulation, processes it in the Vector Signal Analyzer, and gives you access to numerous measurements coming directly from the VSA software to loop back into your system design. This allows for some exciting new capabilities in closed-loop feedback or other types of signal processing that aren't possible directly in the VSA software. Now let's see this improved VSA integration in action. In this demonstration, I'll show you how the PathWave System Design VSA link works. In the past, we've had access to a VSA source and a VSA sync model. But now with this 2022 release, we've created the VSA link component, which is effectively a combination of the source and the sync measurement functions. This allows you to output data from the VSA back into your PathWave System Design schematic. To demonstrate this, we have a simple 16-QAM digital modulation. This is built using standard PathWave System Design components, but you can see what would typically be the VSA sync has been replaced with the VSA link component. The output of this goes into some signal processing and then is output to our traditional sync models. One thing to note is that within the VSA, This runs typically the same way that you would with the VSA sync. However, the measurement will pause automatically so that you can capture the data and it can be sent back into PathWave System Design. In this case, we've set this to pick up data from VSA trace B. If you note, the VSA windows are lettered. So by using the letter that corresponds to your desired measurement, you're able to output that data, in this case the spectrum data, back into PathWave System Design. After running the simulation, we can look at the graph, and you'll see that we've got the exact same spectrum measurement available in PathWave System Design that we saw in the Vector Signal Analyzer software. Obviously, these measurements aren't just limited to spectrum, so you're able to pull any type of measurement from the VSA software and bring that back into your PathWave System Design schematic for further analysis. Thanks for joining us for this preview of PathWave System Design 2022. We've highlighted exciting new advancements in 3 areas: phased array, where we've continued to improve the most advanced RF modeling platform available for phased array analysis for increased simulation realism. We've also made major enhancements in the radar system design workflow, making it easier to configure and visualize complex systems and scenarios to get you to your performance analysis much faster. And finally, we've enhanced the workflow between PathWave System Design and PathWave VSA, giving you that common Keysight measurement science analysis capability and giving you new capabilities for feeding that information back into your system level design. So thank you again, and we're excited to see you when PathWave System Design 2022 ships, helping to deliver your model-based vision. Thanks for joining us for this presentation. What we're going to do now is go into our question and answer session. Okay, let's get on to the question. Here's our first question. I saw that Keysight VSA software has pulse analysis for radar. Can that be used to analyze a system if you're using the new radar interface? Well, yes, absolutely. As I mentioned, you'll be able to run your simulations directly from the GUI, or you can modify and interact with the schematic that was created. Designers can easily insert the VSA sync analysis and then process the results directly in the VSA. You could also couple this with the new VSA link feature and feed those measurements right back into your system design. Okay, our next question asks, do you see the digital engineering and model-based design trends just in aerospace defense, or is this a bigger movement? That's a great question. Yes, this is definitely part of a bigger movement. Projections range dramatically, but as you saw in the keynote, these markets are seen in general to be growing on the order of 40% per year. As an example, companies like Tesla are causing the same kinds of disruptions in automotive that their counterpart SpaceX did in the commercial space world. So yes, I expect to see these trends across all the industries that we serve here at Keysight. Let's see, I see a question here about an earlier presentation. It says, in the talk from Mark Lombardi, he mentioned digital threads. What is their importance and how would someone use your software to simulate such behavior? Well, that's a very keen observation for starters. And digital threads are really a key concept in the area of digital engineering. They connect multiple parts or conditions of a model into what we think is like a predictive behavior. An example would be using the SDK software from ANSYS to design and plan a mission, then coupling that with PathWave Systems Design communication link analysis to test that predicted behavior. You could also consider the evolution of this model once you've received and tested your amplifiers and bring that measured data from your Keysight P&A-X back into PathWave System Design as an X parameter model. I think the key here is that these models evolve over the life cycle of the product. Okay, the next question is, For phased array modeling, is there a limit to the number of groups of elements I can have? So there isn't a practical limitation. You simply need to be able to define the position of each group in the array. Once that's done, like I did in the demo with the group map that I created, the rest is just handled by the simulator. So really, it's up to the complexity or the size of the array that you're attempting to simulate. All right, I think we have time for one more question here. Here's one about the product release itself. Let's see. These features look very useful. When will the 2022 version of PathWave System Design be released? Well, that's a very, very clear question. Our target release date for the 2022 version is the end of August of this year. But if you're a current user of PathWave System Design, you can sign up for our early access program to get access to these new features as they're developed. And you can do that by contacting Peter Blood, who's our PathWave System Design product manager. He can then get you enrolled in the early access program, and you'd be able to join our sprint reviews as well to see demonstrations of these new features. All right, well, that's all we have time for right now, but thank you very much, and we hope you enjoyed the presentation.
Thank you again for attending. Learn about the most advanced RF phased array design and modeling platform brought to you by Keysight Technologies. If you're a current user, be sure to sign up for our Keysight System View users group on LinkedIn. The copyright of the presentation material is owned by Keysight Technologies. I'm Richard Duvall. Thank you for joining and have a great day.